Hello again, everybody. Today we're doing the last of 3 sections that I had set out to do. And this is again a summary of what has been discussed so far and what we're doing now. Alright, specifically we're doing section 9 for product of sum to product formulas. Alright. Again, just to reiterate the past a little bit, I'm sorry to be kind of glossing over it a little bit. It's just that I have a real estate issue here. And I think that if I had an appropriate amount of space, it would be worth taking more time than I have. Anyhow, the sum and difference formulas come from right triangle trigonometry. All right, specifically that as it pertains to a unit circle. In a unit circle, the x value, the x coordinate of a point on the edge of the circle would be simplified to just simply cosine, because the radius would be 1. And similarly, the y coordinate would be sine, because again, r would be 1. If you input these values into the distance formula for 2 different points, right? Because normally the distance formula is the sum of the square of the differences of 2 x's, right? And the differences of 2 y's, right? In the distance formula, you will get a certain distance between the points, right? If you then rotate the angle formed by the endpoints so that one of the sides basically aligns with the x-axis, right? Then you could input a second set of coordinates into the distance formula, right? And you will get 2 distinct distances, right? At least the way that they look is distinct. They are actually the same value. And you can set them equal to each other, right? If you rearrange those distances, all right, you get the sum and distance formulas from them, all right? Similar in the sense that where are these derived from? The double angle formulas come from the sum of 2 angles, specifically when alpha angle and angle beta happen to be the same thing, all right? From the double angle formulas, right, the reduction formulas can be derived, right? And their real purpose is that they translate degree 2 into degree 1, meaning that if you have a trig function that is squared, you can reduce it back to degree 1, which is more or less a normal trig function. Right. And it also, just the only caveat is that when you have a degree 1 trig function in the reduction formula, it happens to be a double angle. Right? The half angle formulas are derived from the reductions, right? And their usage is basically for calculating a half of a special angle. And usually what that means is half of 30 being 15, all right? Or half of 45 being 22.5. Something like that. All right, now today, the product to sum is calculated from basically adding the sum and difference formulas for, say, cosine, combining them, right, by adding. That's visible, it's a little bit faint. Anyhow, if you combined the sum and difference formulas for the same trig function like cosine, what you end up with is something that translates a product to a sum. As for going the other way, this, just to give you kind of an overview here, comes from U substitution, really. U substitution done twice, all right? And so a lot of times what you'll see in a textbook is that they will use U to represent the sum of 2 angles, say something like that, and a V, as it follows U in the alphabet, right, to UV, for difference, right? Manipulating these and the end result of solving for, say, alpha and solving for beta, and then plugging it into the other incarnation of this, all right? Basically what that ends up being is that you have expressions like this. U minus v over 2 and u plus v over 2. Okay, all right. Anyhow, let me spend the balance of time walking you through the problems that would utilize these two formulas, or these two types. I would again suggest that you want to print out this summary, right, specifically this page. This is actually 2 pages. There's another one with the regular triangle guy on it. But we're going to be paying attention to these formulae. Section 9.4, right? Product to sum, and then backwards, sum to product. Okay. Now, the first thing to articulate is, let's write a product as a sum for cosine. Eraser, hopefully. This eraser's nice today. All right, cool. Even blue came off, and not so much over here. Good enough. Let's say we do this. Write a product as a sum, right, and specifically for cosine. Now, if you were given something that looks like this, 2 cosine of the input argument here is 7x over 2, cosine of 3x over 2. All right, what you should do is basically look at the trig functions involved. These are both cosine, and notice that they are pressed together, so one could assume they are a product. So therefore, right, when you are looking at this piece of paper, zero in on the one that involves cosine and cosine. Notice that you have some other choices here. You have sine times cosine, sine times itself, and then cosine in front. All right, we want this one, cosine of alpha times the cosine of beta. It's not perfect, but this is what the model would be. All right, so I'm going to rewrite this on the board. Let's see. So here's the model that you'll be using. And if it's a little faint, I'll write it in a darker marker. Cosine of alpha, cosine of beta is equal to 1/2 cosine of alpha minus beta plus the cosine of alpha plus beta. We're going to have to tweak it slightly, but it's not actually too bad. All right. What you could do, all right, is just convince yourself, all right, this thing that is given to me has that identity tucked into it, right? There are 2 distinct arguments here. You can call this an alpha, you can call this a beta, respectively. They're different. And then just say, all right, well, I'll take this then, right? Since this is filling in the void for the red, right? And multiply it by 2, right? But just remind yourself, you can get away with murder in math as long as you're consistent. So if you start messing around with one side of equals, right? Do the exact same thing to the opposite side and everything is shipshape. So I'm going to squeak a little times 2 in here. And at this point, we could kind of just narrow our focus to the right side of equals, right? Because they're just asking us to translate this, right? We don't have to distribute or anything like that, right? It would be pointless anyhow, right? What we're gonna do is we're gonna tidy up, right? 2 times a half cancels out, it's just 1. And now I'm gonna insert the alpha and the beta. So if 7x over 2 represents alpha, in theory 7x over 2 would be squeaked in here, and also here. And beta will be 3x over 2 in these 2 places, right? Do what simplifying you can, right? But just realize this is going to be pretty much done, right? If they want you to just simply write this product as a sum, given this, this is what it will equal, right? It will be equal to the cosine of these 2 arguments subtracted, and they're like term, pardon me, they're the common denominator is 2, so you don't have to tweak them too much. They're like terms 7x and 3x respectively, and now you are subtracting them, so it's 4x over 2. And then the second cosine is those 2 things added, 7x and 3x are 10x, right? The only thing that you could do now is just simplify the bit of the fraction that is left over. So if you divide both of these by 2, you're just left with 2x for the argument here, and you're left with 5x for the argument here. And this is basically your answer. Okay. Right. Not too bad, right? Here's another type of problem you are inclined to see, an evaluation problem. So, suppose you were asked to evaluate. Yes, you could use your calculator, but you don't have to. All right, it's the whole point of this exercise. You can use identities like so. If you're going to evaluate the cosine of 15 degrees minus the cosine of 75 degrees. Basically, look at what you have handed to you here. I know that it is a difference to be technical, to be perfectly technical, but as for the collection of identities that you would choose from, right, it's something that would be analogous to a sum. So again, if you zero in on the sheet here, let's go down here where you see sums to products, right? This isn't appropriate because it has a plus. Here we have a minus, right? In this case, we also have 2 cosines, so we would have to be more specific and choose this option here, cosine of alpha minus cosine of beta. And this is what the identity works out to be as a product. Okay, so let's replicate that model. I may have to switch markers here, so I think that it's fading out. Okay. All right, the marker here, pardon me, the formula here, for one-track mind. Cosine of alpha minus the cosine of beta is equal to negative, let's see, do I have to go that far? Yes, I do. 2 sine of the argument alpha plus beta over 2 and sine of alpha minus beta over 2. Let me just make sure I replicated that correctly. That looks good. Okay. All right. Now at this point, we're going to employ a little substitution. And if we see anything familiar, like 30, 60, 90, 45, any of these special right triangle angles then we could employ those ratios. Anyhow, if I understand that this is, I'll just call this alpha just because it came first, and this beta because it came second, and then insert them into the identity. So if we have 15 squeak in here and 75, right? And then over here it's 15 minus 75, right? What does that mean, right? And this is representing this specific problem here, right? At this point, you can just pay attention to the right side of equals exclusively, right? Because you're basically using this to calculate. Right? Anyhow, minus 2, this is really the sign of the outcome here. 15 plus 75 is really 90. What is half of 90? 45, right? Degrees. 15 minus 75 is really 60. That happens to be negative 60, right? Half of 60 would be 30. So this is the sign of negative 30. Okay. Now here's where, again, right triangle trigonometry of special right triangles would be handy. There are two types usually, right? There's the 30, 60, 90, and the 45, 45, 90. Right? And the angle relationships of the 30, 60, 90 are square root of 3 along the edge that is 30 and 90, and 1 along the edge that is 60 and 90, and 2. For the 45, 45, 90, remember that it is 1, 1, and the square root of 2. And in this case, we could translate, stop picking that up. We could translate 45 into the trig ratio that is appropriate. All right, let's just say that it's regular positive 45, so opposite, right, over hypotenuse. Right. The opposite of either one of the 45s, I'm just going to go with this one, is 1. And the hypotenuse is the square root of 2. We may have to rationalize that denominator later, but let's leave it alone for right now. Still have this free-floating negative 2 here. We'll do a similar thing. We'll translate sine of negative 30. Now, the only thing that you really need to adjust is the sign of the ratio that is produced from this, right? If it was just regular 30 degrees, right, then it would be along the, in quadrant 1, along the positive x-axis here, the positive portion of the x-axis. All right. If it's negative 30, in theory, it's still along the positive x-axis, but the y value, instead of going up here, goes down, right? It would be in quadrant 4, specifically. I don't know if that's very hard to see or not. On a coordinate plane is what I mean. This is y, this is x. If it's positive 1 for this dimension up this side of the triangle, then negative 30 would be negative 1. Okay? And it's still a square, pardon me, it's still the hypotenuse of 2. It's just pointing down. Anyhow, what does that mean in terms of this ratio here? It would still be an opposite over hypotenuse. Right? So the opposite of negative 30, if you can imagine this as being negative 30 degrees, opposite of that would be negative 1. Right? Just that one adjustment. Right? And the hypotenuse would still be 2. One other little tweak here, little adjustment, is rationalizing the denominator, right, of the square root of 2 here. What that really means is that you're going to be taking square root of 2 and placing it on top, because you're going to multiply, this is to rationalize, a denominator you're going to multiply this ratio by 1, a convenient incarnation of 1. So if it was 1 over the square root of 2, then you're going to multiply by a convenient ratio of 1, that is to disguise the amount of 1 so that it manipulates the situation to our advantage, right? Usually what that means, especially in the case of something that's one term wide, you know, sort of a monomial, I really can't call it that, but it's just one sort of chunk, right? And that's a square root. You're going to multiply it by itself, right? But to make it legal, whatever you do to the bottom, do also to the top, right? And the effect is that you end up with this, right? 1 times the square root of 2 now is above the line. And then the square root of 2 times the square root of 2 is itself squared, right? Which cancels the square root, because they're opposite operations. So you're just left with regular 2. Okay. Now, if you are just these three elements, the square root of 2 over 2 now, and now the negative 1/2 are being multiplied, and you could just make negative 2 look like a fraction by sticking a 1 under it, you can do brute force multiplication, which is the top times the top, and then write what the outcome is. The bottom times the bottom, and write what the outcome is. There's no, and then simplify as an afterthought. But it might be more strategic to go, well, these 2's can cancel, all right, and that would leave a 1 here. They have the same factor, and one of them is sitting above the line technically, and one of them is sitting below the line now. So that would be a negative 1 times the square root of 2 times a negative 1, which is a positive square root of 2. And then 1 times 1 times 2 is 2. This would be the value that you have, the square root of 2 over 2, all right? As proof of that, all right? Let me walk you through using your calculator just to validate. All right? Just make sure that your calculator is in degree mode. All right? If you were to enter this value, cosine of 15 degrees minus the cosine of 75 degrees, we'll see what the decimal equivalent will be. Cosine of 15 minus the cosine of 75. We will establish 0.707, which is, after a while, becomes a familiar decimal because you see that value a lot. All right, now, if the calculation is correct here, square root of 2 over 2, we should get the same decimal, and I want to say that it is. So I'm going to hit second and then square to get the blue square root behind it. Input a 2, move out of it, hit division, and then hit 2, and then hit enter. And you see we get identical decimals. So it's all good, right? And again, the advantage to doing it this way is, although they didn't specify, I didn't specify because I wrote it, but I stole it from someplace else. They didn't say, get an exact answer, all right? They normally say that. Why? Because you end up with an irrational number, right? And an irrational number is infinitely stretching. So that is a better answer, arguably, than the decimal, right? Because the calculator has to chop off infinity at some point. It'll give you, a high degree of precision, but it can't give you all of infinity. That's just impossible. Okay. One more of these. All right. Let's say that you start with a product and you want to evaluate the product using a sum or a difference. So in this case, suppose you were to evaluate the cosine of 45 degrees times the cosine of 15 degrees. And again, start by examining what is given to you. I draw an eyeball to go, look at this, you know. Maybe I should draw 2 eyeballs instead of 1. Looks a little extra crazy, right? You know, I kind of like that. I don't draw 2 eyes too often. I usually just draw 1. Right? But together they look even more nuts than normal. Right? Anyhow, you notice that you have a product because these things are pressed together. And they're both cosine. So again, if you take the resource that you have, picking up that marker, all right, and zero in on where you have products, not to beat a dead horse here, this happens to be cosine and cosine, right, of 2 distinct angles, so alpha and beta respectively. All right, that means that if you had to evaluate it, you have the option of translating it into this sum technically, because there's a plus here. All right, 1/2 the cosine of the angle subtracted plus the cosine of the angles added. Okay, so here's the model that we will input. The cosine of alpha times the cosine of beta, in parentheses would be nice, is equal to, this is going to squeak in here, the cosine of the difference plus the cosine of the sum. And just make sure that I replicated that correctly. Yes, it looks legit. Okay. So now we will make it conform to our specific situation. If this is an alpha and this is a beta, and this is a 45 here and a 15 here. Right? That means that we will subtract 15 from 45 in this case, and we will add 15 to 45 in this case. Right? And at this point, you really just need to pay attention again to the right side because you're trying to evaluate it using a sum. Right? So this would stretch out to 1/2 the quantity of the cosine of, let's see what this reduces to. 15 minus, pardon me, 45 minus 15 is really 30 degrees, plus the cosine of 45 plus 15 is 60 degrees. Okay. And we can figure out what the trigonometric ratios would be for each of these. They're special triangles, right? So, a little thought cloud here. The only special right triangle that we need to employ is the 30. I'm exaggerating it when I shouldn't, but the 30, 60, 90. Again, along the edge of the 30 is the square root of 3, along the edge of the 60 is 1, and the hypotenuse is 2. So, nothing to worry about in terms of a negative angle. That would be would be clockwise as opposed to counterclockwise, which is normal. Cosine is adjacent over hypotenuse. So, in terms of the ratio, fraction, whatever you want to say, all right. In respect of 30, right, the dimension that is adjacent to 30 is the square root of 3, and the hypotenuse is 2. And then, inputting this, in respect of 60, you would need to sort of remember that you have a 60 instead of a 30 in this case. Adjacent, because this is still a cosine, adjacent to 60 would be 1. Okay. So we're going to have 1 over the same hypotenuse of 2. Which means that you don't have to worry about converting the denominators at all. But now, remind yourself that there's still this, I keep picking up that marker, there's still this half sitting outside here. Could you distribute these two? Yeah. Would it be to your advantage to do that? It wouldn't hurt either way, it would seem. Right. Technically, if this is inside of a parentheses, I gotta throw that away. You would combine these into one fraction, right? So, since they have a common denominator, the option that you have is to do this. So write it as the square root of 3 plus 1 sitting on top of 2, and there's still this 1/2 on the outside. I'm just opting for a different style of bracket, okay? So then it's top times top and bottom times bottom, and the end result is this. The square root of 3 plus 1 over 4. Okay. And again, just to verify that this is an exact answer of what this would produce as using a decimal. Okay. We have the cosine of 45 times the cosine of 15. Okay, you will see that this produces the decimal of 0.683. And this is what we get if we use the sum instead of the product. So the square root of 3, I gotta be careful with my syntax here. Delete. Parentheses, no, different. It's easier to do this while actually looking at it, okay, rather than looking at it backwards. Divided by 4. Okay. This is how I've entered it into the calculator. I grouped the top, right? And there's the same decimal. 0.683, what it is into infinity. Right? In this style of writing it, it's a more exact, it is an exact answer because it involves an irrational number. Right? This is just a high degree of precision. All right. Okay. Right. And that's actually it. Right. As I said originally, I had intended to do this over the course of just one day, really, rather than do it up and break it up into 3 segments. And it's better, I think, because we can just explore these things a little bit easier. Anyhow, I'm going to upload now. Again, keep this resource, it's invaluable. All right, next week will be the last week that we have new materials. So I'm going to do section 10.1 on Tuesday and 10.2 on Thursday. All right, and then I'll tell you what's going to happen with the final. Okay? All right, I'll see you later. Thank you for tuning in. Take care.